everybody. Thank you very much for having me here. This is a really exciting conference, and I think that it's really great that what's going on, both in this community and open source, is very exciting. The relevance of big data to the open source space is really quite high because you could say that actually open source is one of the things that help make big data happen. I mean, big data, which we'll talk about some of the things that make it interesting, but one of the things is that the relationship to big data and open source is pretty high. And earlier today, one of the first big presentations had about how open source is related to cloud, it's open to mobile, it's open to social. And there was a question, how about big data? Actually, we even have a connection there, but also it goes back that they reinforce each other, because the more things that happen in the open source world, the more ways people can take advantage of the data. Now, one of the things that's kind of interesting is that this data is really coming from everywhere. And the place where people are spending a lot of time talking about it right now is like the Facebook and the Twitter, social media. But actually, it's coming from everything, because what we're doing is we're putting, in effect, computers everywhere. Right? You've probably heard about like Internet Zero, the Internet of everything. As long as things become more and more connected and the value of that connection increases, that means that the data is going to be coming from more and more places. And so sensor data that can include just sensors, as in the basic stuff people think of, like temperature, but we'll see how sensors and monitors are important. RFIDs are something that is radio frequency IDs, or just the less expensive version, the barcodes, the QR reader codes, all that plays a role in big data. Mobile phones play a role in big data, as in mobile devices, because what people are basically doing is they're carrying around in their pocket, in fact, one of the most complicated mobile sensors and mobile data producers that there can be. And then also things like social media and stock exchanges and things like that. If you think of stock exchanges and commodity exchanges almost like voting machines, people, instead of one person and one vote, it's basically one share, one vote. Those are also huge sources of data, and people want to figure out, well, if all this stuff is happening, what can I do that will basically do two parts? One, can I understand what's happening? And two, can I make a prediction about what will happen next? And the ability to understand what's going on and predict things, what we call now is, we call that analytics. And that means analyzing the data, looking for insight. Sometimes we call it insight, which is what you get after you do analytics, is you'd have some insight into what's happening, who's saying what, why are they saying it. And what we'll do is we'll talk about how this big data and the open source come together, and also how IBM is helping in that process as well. So first of all, one of the things that somebody goes is, well, why would even somebody want to work on big data? Part of it is because people are really asking for it. People are saying, I've got all this data that I know that there's something useful in it, but I can't figure out what it is. And every day somebody has to make decisions about what to do. If it's as simple as, you're trying to decide, should I do my errand first and go to work, or should I do my errand after work, or rearrange things? Well, but you may need a little bit of information. So that's one decision, but you're kind of forced to make that decision because the time is always on a constant clock. Time is always happening. You have to make a decision, ready or not. And so if you have the data and you have the insight in advance, then you can make a better decision. So a lot of people, when we've done surveys of basically the top 1,000 companies and asking them, what do you think about your ability to make decisions? A lot of them say, well, we do have these large IT departments, but the problem is that there's still a lot of information that's not in those departments or not processed that we know would help us make a better decision. So then the first thing that people talk about is, how do you characterize this data so that you could find the capabilities to find what value is inside. So we have three ways that we talk about it: volume, variety, and velocity. And volume is the one that people think about the most. Volume is how much data. And if you were to do something like record as an MP3 file all of human speech, basically from the time that we think people started talking till now, you'd get basically like a zettabyte. That would be your music library. You could listen to anything everybody said throughout history if you had that zettabyte of data. Now, the amount of information, though, is kind of growing at an exponential curve. It's not because of just the amount of computers that are there, but it's also because the ability for people to capture it, transmit it, connect it, and that leads to, in effect, an explosion of data. And this data, sometimes people call it unstructured data. Any data, whether you know its structure or not, the structure can move, the structure can change. Where you have to extract the information, whether or not you really know that much about the structure, are some of the reasons why the volume of unstructured data is growing faster than almost anything. Now, variety is about the kinds of different sources of information. You can get information from many places in many different ways, but if you think about it, if you were to, say, open up an encyclopedia versus open the newspaper versus open social media versus taking a phone call versus watching a movie, all of those actually have human understandable information, but it's all in completely different forms. You need to do something like do a natural language process to extract that information into a form that the computer can understand. The last aspect is velocity. Velocity is about the rate at which data arrives, and not just the faster networks, but as anyone who looks at, for example, social media, there's more and more of events that people are creating being produced every day. Computers go faster, more of that's being produced every day. Things are being connected. The velocity is important because if you can't keep up with the rate of the data that's coming to you, then also that would be a way of getting behind. And if you think about it, the ability to keep up with this data becomes really, really key. So here's some of the statistics about things in volume, variety, and velocity. In effect, there's really terabytes of tweets, computer power meter readings. Everybody now has a smart meter attached to their residence versus an old style, just a bar meter. Velocity, the amount of information that's coming in. And then the question is, like, what would you do if you had this information? So, for example, with variety, you could do things like understand what's happening. You could have a better security system, or you could find what's what's being videotaped. For call detail records, almost everybody has a place where people can come in and send their input saying something's working, something's not working. Frequently at companies, that's a call data center. Being able to have the people at the call data center actually understand the problem by the time the customer calls in is really key. Often there's indications in the network that maybe there is a problem, drop calls from, let's say, mobile phones, but the information needs to percolate in so that the person at the call center is prepared not only to answer that question, but also to do the things it takes to retain that customer. So I'm going to give in this a few examples of volume, variety, and velocity about what makes big data, and then how is open source helping to tame that. So first of all, in the IBM Watson game show, IBM had a computer called Watson. It played a game called Jeopardy. How is that tied to big data? Well, it's really tied to big data through the concept of variety. You have in the kinds of information that people have to understand to answer simple questions, and sometimes tricky questions that are played in this game of Jeopardy, you really have to have an understanding of the facts of the world and recent information, historical information. The kinds of information that goes into it is actually very huge. And so there was a contest set up that was a grand challenge to try and see whether or not a computer is capable of answering the kinds of questions that human beings are very good at. And how did that happen? It was done by, in effect, preparing by looking at big data, setting things up so the computer had some information, and then playing the Jeopardy game. In this game, we had the Watson computer contestant with the two best Jeopardy contestants from all time. One of them had won 74 consecutive games. Another one had won the most money and had never actually been defeated. And they brought these guys together all for a game where where the way Jeopardy works is you pick a category, you pick an amount of money to bet on, and then you try and make an educated guess, and whoever is first with the right answer is the winner of that particular round you keep playing. So Jeopardy about a year ago had this grand challenge, and Watson was able to come out with the leading answers, and that was done basically by use of big data. What happened was, in advance, a whole bunch of information was taken from its original sources. That's encyclopedias, almanacs, newspapers, movie databases, sports databases, all sorts of feeds, so that people can ask questions about really anything in the knowledge domain. Many millions of pages of text were loaded, and to help do some of this processing was one of the key foundations to open source in big data, which is the Hadoop project from Apache. And we'll talk more about how Hadoop is used. But what it effectively did was look at data from a variety of different sources in its regular context. We had also some text analytics, which was added on top of the open source, and a bunch of analytics that were based on this concept of machine learning and predictive analytics, where the data was processed, clustered to try and figure out which categories different information went in. And what happens in this system is the information is processed, hypotheses are formed, in effect indexed so that when the question actually arrives, the system running on a very, very large cluster can go off in parallel, ask questions in parallel, rate the hypotheses in parallel, and then the most confident hypothesis is the one that is actually picked to answer the question. And actually, in Jeopardy parlance, that would be to provide the right question for the Jeopardy answer, because they turn this on its head and use a number of puns to make it a little bit more complicated. But the ability for the computer to understand natural language processing, takes these questions in real time and return real responses, was key. And it resulted in a number of real advances that were based on the open source of using big data, plus text analytic processing, and plus a large cluster. And one of the aspects that's key to big data processing is often a high amount of parallelism that you get by running many computers together. And IBM built a special cluster for this, but big data frequently runs on clusters that are kind of similar, a whole series of parallel computer nodes that are all linked together to carry out a higher task. So I'll talk a little bit about what is in the text analytics. So if you look in the upper right corner, you see a picture of some text that comes from there's unstructured text that comes from a report about the World Cup 2010. And if you look at the color coding, by reading this text in its natural form, and then you can actually construct, in effect, a table of knowledge about what was happening. What is the country, which is in blue, what position in soccer was being played, which is in green, and the names of the different players. And so this is done by having text analytics that's running in parallel across multiple nodes, handling different documents in parallel, and then breaking out and, in fact, finding structure from the unstructured information. And so text analytics is one of the key use cases or key technologies that makes most of the use cases around big data and social media especially relevant. So if we go down, what I'll show is some examples of how this can be extracted from social media. It's okay to not be able to read these individual events, but what we're going to show is several different events that are coming in on Facebook, and then we'll show some for Twitter. And what you're seeing in the first one is somebody saying happy birthday, very nice to have your birthday, some other information about songs, iPhones, and then a comment that really doesn't have much meaning at all. And by using text analytics, you're able to go through and find information about what's relevant, what's not relevant, and this thing monetizable intent that someone says, I'm sick of my phone, I'm going to buy another one. And it is interesting that by reading language and doing natural language processing, you can actually find out a lot of useful things that, that can be extremely helpful to understand and make use of this data. So if you think about what's going on also for Twitter, over here someone's saying we're going to go meet together at a particular location. Another section is talking about that we're going to move. Another section is talking about somebody who thinks that they're going to be doing something. And then, of course, you always want to get rid of the spam. That's one of the enduring qualities of many things, is that spam is also one of the aspects that there's a lot of noise, and you always want to just focus down on what's the real signal within that data. So part of big data, finding what's real, finding, in effect, what's the needle and what's just the hay in the haystack. So the combination of looking at things with basic text processing allows you to come together and synthesize information that you could get over multiple tweets or multiple events, multiple social events. And this is pretty important because it allows somebody to get, in effect, a 360-degree picture about what's going on. And by bringing information together from multiple sources, you can actually help a lot. And if you are a customer who has been using, let's say, a retail website, and you're at a retail site and the customer's been writing reviews of things, then you could look and you could say, well, my customer has been writing things where they like some products, they don't like other products. You could decide for maybe they should get some coupons for products they like or products they might like. And you see things like that in things like movie suggestions. What movie would you like to watch next? And a large amount of information is based on analyzing different small individual needles, bring them together to try and make a cluster or a picture of what's really happening. Now, it's not necessarily, though, just about analyzing social information. Also, one of the ways that you can use this is an example of velocity. And in velocity, it's showing high rate of information from big data coming in, processing it very quickly. So what you have in hospitals is they have intensive care units where premature babies spend some of their first days when they're born very early. And they're hooked up already to a large number of sensors to make sure that everything's going fine for these very little kids. They have often a number of sensors which are hooked up to do blood pressure, to do their heart rate, to do carbon dioxide. It's very important to make sure that everything is going quickly and correctly. Now let me see if I can run a video. It's very, very short, and we'll see whether or not it works. You cannot hear the sound, unfortunately. All right, well, what this video is showing is a very premature baby surrounded by sensors with where the sensor information is being processed and synthesized together to make sure that
do what they're doing in Toronto and build a smarter hospital. Let's build a smarter.
Let's do that one again then.
This is a baby generating data in a neonatal ward. Every heartbeat, every breath, every anomaly, from over 1,000 pieces of unique information per second, helping doctors find new ways to detect life-threatening infections up to 24 hours sooner. On a smarter planet, analyze the data and you can predict what will happen faster, so you can do what they're doing in Toronto and build a smarter hospital. Let's build a smarter planet.
So what was done to help this young baby was, and all the babies in this hospital, was to take the sensors that they were already hooked up to and process them in parallel and look for certain well-known conditions which could lead to, in this case, the onset of bacterial infection. Bacterial infection can be very serious because in order to remove an infection can require adding a lot of drugs which could have side effects. You really don't want to have to do that, especially in a reactive mode for these extremely young children. So by finding the right correlations and correlating the sensor data immediately, basically on an instantaneous basis, we're able to help these children by signaling the onset of infection at the earliest possible sign, when the first set of sensors has that right correlation. And that means that you can signal and bring over a medical professional, and they were able to find that they could find these infections up to 24 hours in advance, and for little babies, this can really help save lives. And so, in effect, big data and processing of this information at high speed was able to make a real effective outcome in helping. What's key about this is that the different kinds of places where big data can be applied is really, really huge, and the opportunities to really make a very positive difference are there. Now, big data actually can be applied to a lot of different places. We saw the smarter healthcare, but it can be used in so many different environments. A lot of work in telecommunications to help people find drop calls, to find when customers are happy or not happy, to help with fraud and risk. When a credit card or other purchase is run, there's only a very small window in which you can make a decision whether it's whether that particular charge is good or fraudulent. And often the fraudulent charges happen in bursts. And you might find that one is okay, but then immediately after there's 3 more. You don't want to wait a long time before you figure this out. So what you can do with this high-speed big data processing is actually, once you start detecting these anomalies in real time, really do more in-depth processing much more quickly, right closer to when the problems are happening. The ability to do things, for example, traffic control is an area that I'll be showing a little bit farther down, reducing congestion, which helps both reduce pollution and make sure that people are able to use the scarce resources of the roads properly. So since there's so many different aspects of big data and there's a lot of different places where it's helping, the first question is well, okay, why weren't we doing this before? If it was really such a good idea, then it should have already been happening. But there's a reason why it couldn't have really happened before, and I'll give an example why, for example, using this gold mining analogy. So if you go back to the gold rush, in fact, the gold rush of California in the 1849s, where the 49er name came from, there was a lot of gold, and it was in very, very high density, just sitting right out in the rivers and the streams. And it was effective. If you could go there and scoop it up, you could get gold. Now, it didn't take very long for people to gather all of this gold, and so it became harder and harder to get gold easily. But the gold was actually not just scattered up in the streams in large chunks. It was actually also buried in the ground. So the next thing people did was they started digging, and they could dig as long as they could see the gold. They would call it a gold vein. And if they could see gold, and as they kept digging, they just keep trying to dig in the direction where they could just see more gold. And as long as they could do that, they were okay. This is mostly doing things like digging by candlelight, because once you got down into the holes, candles and kerosene lamps and things like that were all they had to see. So the gold had to be really very high density for it to be economically profitable. But if you fast forward that, they got more and more automation, more and more machinery, until eventually now people can collect gold and process this gold efficiently at extremely high scale. They have very large machines. The machines are in effect parallel processing by scooping up huge amounts of dirt, extracting the gold. Even though people can't necessarily see it, it can be extracted and condensed. And this is in effect there's 2 aspects. One is the application of parallel processing, multiple tractors, multiple systems. Also the aspect of where the economics are. The economics of one guy was such that he could afford to do it himself, but he couldn't afford much more than that. But as the price of gold relative to the cost of having more and more automation, more and more machinery, made that point change, gold mines open, they close, their capacity expands, contracts continually based on fluctuations on the actual price of gold. And so the economics, the cutoff level, when is it worth doing, when is it not worth doing, the mining systems have gotten very flexible that as long as people know when it is worth doing, when it's not worth doing, you can then adapt and process or not process that gold. Now, the analogy back to computers is if you think about valuable data within the actual total set of data you have. The way relational databases are primarily set up now is that the data that's in them is mostly considered extremely valuable. The transactional databases, people spend a lot of energy making sure that they're always up to date, that they have great transactional semantics, they have the ability for multiple users to be looking at different views simultaneously, all with great consistency. All sorts of very key aspects of that processing are designed to make sure that the integrity of that data is in effect always perfectly high density gold. And that's great, but there's a lot more data in the world than just in the form of already purified high density gold. There's data that is in much lower densities. So what people have come up with over the years is a bunch of processes that are now called ETL, extract, transform, load, take data from a whole bunch of different places, that's extract, transform it down until it's good enough for the database, and then load to put it into the database. And the idea is that the databases are then always supposed to have gold data. Then you end up with large chains of ETL processes all feeding in. Now, this is good as long as you're really, really certain you're going to be able to get gold out and you're willing to put in the investment, knowing up front, by making an upfront decision that gold will be there. With big data, it really lowers that economic barrier, just like the gold mining, by applying parallelism to reduce the cost and be able to work more smoothly with unstructured and lower density data, where the lower density of gold in that data, so that you can sift through the spam or just the regular dirt to find that gold in parallel much more quickly. And so in terms of a more computer way of looking at it, the traditional approach, which is working just fine, and it's very, very good, has all these really, really well-known established technologies. Hierarchical databases, relational databases, transaction processors, message queuing systems, enterprise service buses, online analytic processing, OLAP. All of these are great established systems that are primarily around a smaller number of nodes that have extremely powerful processing ability and are working on high-quality data. What's emerging more and more in this big data space is processing a large amount of data on less powerful individual nodes, then using those individual nodes and sorting through the data to stream and combine the information back up. The first major use of this kind of processing was done in search engines, and a lot of search engine technology is extremely parallel. Crawlers are in parallel, indexing is in parallel, reverse indexing is parallel, serving up the data is in parallel, and the analysis was based on early use of the MapReduce algorithm, which eventually became part of the open source projects, but also the analysis, this quote PageRank algorithm, for example, that Google had, was key because the analysis, the analytics on that data was extremely important, having the right algorithms and applying them correctly. So the combination of these new technologies, MapReduce, stream processing, the Watson-oriented processing, which we talked about, I should have mentioned as we call it deep QA, deep question and answer, because question and answer processing is where somebody can answer an open-ended question, and deep QA is a new kind of processing of this large data. And what we have been doing in IBM research for many years is we've been calling it massive scale analytics. What would happen if you had the ability to process huge amounts of data in parallel? And so the combination of all of these are coming together, and people are building ways to package this up and make it more consumable for people to leverage these technologies. And so at IBM, we call that the Big Data Platform, which is an aggregation of the analytic technologies and the open source technologies together to bring it to the point where it's easy for people to get value out of this data on their own. Another aspect of what makes this different between the traditional approach and the new approach is how much upfront understanding of the information has to be there. For the regular traditional processing systems, a lot of it is based around the concept that you have done something like decided what the schema of your data is. The corresponding thing is deciding what your data structures are. What is your relational table? What are your structs? What are your classes? Knowing a lot of that up front is something people put a lot of energy into with the traditional processing. But with the approach where you're not always sure what you're going to see in advance, where you have to have, in effect, flexible structures where the data comes in and you have to analyze it in its original form, not in the form that you wish, is extremely challenging. And that these come together because often you can extract from the unstructured form forms that matter to you. And the combination of them together is often you do things like process the data in this unstructured form and then condense it and make, in effect, take the low density data, find the gold, and put it into the high density existing structured systems. So the big data open source projects, there's obviously a lot of projects, so what I just am highlighting are some of the most popular projects. Now most of the time, most of the energy people pay attention to is the runtime itself. The runtime environment is based on some key projects, and a lot of them are now at apache.org, Apache being one of the main places where people do open source that is around runtimes, especially when the runtimes are written in Java. Apache got some of its original attention through its HTTP server, but then over time there were additional projects. Lucene is a very key project that's been in Apache for a while, which is a high-performance text index. And then there's a bunch of these new projects. Hadoop is the one that is the most popular project. It has really two parts. It has a MapReduce part and an HDFS part, the Hadoop distributed file system. Hadoop is kind of a funny name. It got its name because the original contributor to the project named Hadoop after what their son called their elephant. It was a little pet elephant, a little cute toy yellow elephant, and you actually see now in the Apache trademarked logo, you'll actually see that elephant around. And that sort of set up that pattern where people would name the other projects that were going to be related to Hadoop with animal-oriented names. So Hive is a project that's about taking SQL-oriented queries and then converting them into processing that actually runs in the Hadoop MapReduce system. Pig is a data flow language, which is another animal. Its purpose is also to write things at a slightly higher level. It's a unique language, but the purpose is process data at a little bit higher, sort of scripting-like level, but what happens underneath is the scripts get interpreted and it pumps out MapReduce jobs underneath. Zookeeper is also related, another animal-oriented name, where the point is to coordinate lots of processes across the cluster. When you have clusters with thousands of nodes, it's very, very critical to have them stay in sync at all times. So the processing of all of these different open source systems together really brings together what people call the core open source technologies. At the same time, people are actively developing with these core open source technologies, and so I'll bring out that the Eclipse integrated development environment is already the most popular development environment for Java programming for people who like IDEs. And Jazz is a collaboration environment, which is kind of open source. It's actually visible source, but it's extremely popular because it's an open collaboration environment, and people do a lot of collaboration when they're building projects in open source in general. And then the Jetty server is used actually frequently throughout the runtime, running many of these services across the cluster. So I'll just quickly mention, how does a MapReduce work? What happens is you take horizontal and vertical slices through the data. So if you imagine your original content was the words hello world, goodbye world, hello IBM. Well, and you were doing the famous word count example. The mapper would take one slice horizontally, finding for each word, it would say, I found this word, found this word, found this word. 1 will always be, the count that it found as it went through. Then the reducer goes across all of the outputs that the mappers produce vertically, and then sums up for every hello, goodbye, then it'll see how many counts it has. By taking these horizontal and vertical slices repeatedly across huge amounts of data, you're able to make these extremely individual parallel processing tasks work together, and you have, in effect, the emergent behavior of that the whole system is running little tasks in parallel efficiently. Now, IBM has been participating in open source for many years. We have over 700 contributors to some of the major projects at Linux, Apache, Eclipse, and most of the major platforms that IBM builds are actually based around pure open source where IBM contributes to, as well as then packages and builds on top of. So the big data platform that we're building at IBM has software from Apache and Eclipse. WebSphere has been long based on Apache HTTP server. Geronimo is another Apache project. Rational, all of the tools like RAD, Rational Application Developer, there's a family of development tools are based on Eclipse and Jazz. And the InfoSphere product line, which are tools for databases, is also based on Apache and Eclipse. And so the combination of all this open source has really led to not only critical aspects of how to process information, but also products are all based around open source. So just very quickly, I will mention that IBM has a big data platform that's built around the open source projects, and then adds on top of it the enterprise engines for processing data in motion. We call that streaming processing, and data at rest, internet scale analytics, that's based on Hadoop, HBase, Zookeeper, and all the Apache projects. On top of it, we have environments to bring together the teams of users that are actually going to be using this, developers who will be building the products that run the analysis, end users, which are actually looking at the results, guiding the system, figuring out what they need to discover and what needs to be analyzed, and then administrators to keep it up, running, make sure the performance is good. And one of the other key aspects of this is managing the data well. If you were to paraphrase the popular saying from Spider-Man, with great data comes great responsibility. If you have all this data, you have to be extremely careful that it's done well. And then, of course, we have a lot of integration with many, many different technologies, because all the technologies that people have already need to be interacting with the big data. And of course, we have about 100 partners where the partners are building their own solutions on top of this platform. So this is showing one of the key use cases of big data in terms of getting data from many, many different sources, analyzing it in the big data platform, using it with traditional databases and other traditional sources, and then finally analyzing on top. And business intelligence is frequently then driving off the relational databases. And over time, of course, more and more will drive directly off of the big data platform as well. Think of it as whatever people are already doing in their systems, unless they actually were misusing existing technology, they probably need to keep doing whatever they were doing. But think of the big data as an additional capability to do things that really couldn't have been done before. Either they couldn't have been done because it wasn't practical, or because the economics didn't make sense, or people didn't have the tools, but taking on these new use cases. The ability to handle information from many different sources is one of the keys, because then you can bring all your data in to the big data section. The storage costs in big data are much lower than the storage costs in other systems, because the data is stored, typically it's an original format, in files on disks arrayed in the system, and that allows huge amounts of information to be processed and analyzed in its original location. And that's actually key, because a lot of times when people are doing long computational chains like extract, transform, load, lineage, where did that data come from, is key. And if you have it all inside of a big data cluster, it's easier to go back to that original data. So I'll show you also the volume example. The volume of of information can be huge, and one of the ways we helped was with green energy. Vestas is one of the largest companies in the world for producing green energy, and they focus on wind-based green energy. So many of the large windmills that people have seen produced are large windmills that have to be placed in exactly the right location to at the right height, the right direction, the right angle, the right spacing, so that they can really actually capture the energy necessary to justify the extremely large capital expenses that are going to be required to, not just build the windmills, but also place the windmills and wire them up to the power grid. And so it's extremely key that before the windmill is actually put in the ground, that you know exactly what's going to happen. If you don't do that, then you'll be in a situation where in effect, a lot of the money that went into producing that green energy plant won't have the economic payoff that justifies building it. So what they do at Vestas is they analyze petabytes of information by taking weather information, information from other sensors, dividing all sorts of places around the world, on land, in the ocean, into different grids, and then analyzing it deeply to find out what's the humidity, what's the temperature. It's not just how much wind is blowing, but how gusty it is. Does it ramp up quickly? Is it more of a constant wind? All these things are really necessary to make sure that the windmill placement is right. And what we've been able to do by helping them is reduce the amount of time it takes to analyze their data by 97% by doing this parallel processing. And so that's an example of large volumes of data that are used to help. And so the volume, the variety, and the velocity are all aspects which big data can be applied to. I'll just give one more quick example. Traffic flow management. We've done this in the city of Kyoto and the city of Stockholm, Sweden, where by analyzing sensor data from where all the cars are, where they're going, how fast they're going, you can also find out how many cars there's going to be for Sweden. That was used for congestion-based pricing, and also it can be used to reroute traffic and make the city flow more efficiently. And so that is both a volume and variety example together, because it's both a huge amount of information, many different kinds of information, and you also have to keep up with it, so that's some velocity as well. So the point of all of this different analysis is to bring the many different components together to handle these important use cases, which are really helping transform things in the world to be a better place, are based on bringing together open source, analytics, and a whole variety of key aspects to managing this data, such as security. You also want to optimize performance, make sure that you have high availability of the overall system, and bring all that together so that it's easy for people to then leverage and apply it more directly to all of the specific use cases. The ability for people to put all this together means that it also makes it a lot simpler, because based on open source, if people need to leverage some of the newest advances that are happening in open source or make changes, a lot of that is possible because we keep up with open source. We're part of the open source community. We have a number of committers as well. And then the integration aspect of bringing together different projects from different organizations, also all developing on their own time schedules, and do that integration. And so the combination of these things helps make big data more practical, more possible, and it's part of what IBM has been calling Smarter Planet. Smarter computing for big data is really a key message. When you see other Smarter Planet different advertisements or different use cases, how different places have been helped by big data, whether it's law enforcement, city management, smarter building management, reducing energy costs, all of those different cases, an increasing number of them are coming from big data and this big data processing. Now, just to wrap up, you can run big data in the cloud. We have the ability to run on Amazon, Rackspace, and a number of other popular places. IBM has a cloud as well. And there's a free course on big data, one of the places where I believe we actually have more registrants for Big Data University than almost any other online course. And so the ability to use this stuff for free in the cloud is one of the aspects that makes it really easy to get started. And of course, big data is a key focus of IBM as it is, where the key is that this is an area for innovation. It's an area for open partnership, an area of participation with the open source community, and I think a place where we can really help the world be better, as you've seen through some of these examples of helping children through and green energy through variety, velocity, and volume. So thank you very much. I really appreciate the opportunity to talk with you, and looking forward to working with you all on open source. Thanks.
Thank you, Dr. Brodsky. I know that in our work with the government that big data that's what they're all about right now. We have one change to the agenda. The gentleman that was doing the education track earlier he has got a mild case of pneumonia, which has put him in the hospital. And so keep him in our thoughts and prayers. And at 4 o'clock, Deb Bryant and Jim Chagowski are going to do an update on the open source initiative, the OSI. Deb, where are you? Newest member of the OSI board. Congratulations. And that, OSI, they maintain and manage the definition of open source and all the license stuff. So anyway, don't forget to go by, say thank you to the sponsors. The next tracks will start in just a few minutes. It'll go to 4:45, where we'll give away the tablet, and then GitHub free beer. Don't forget, thank you.